Hi everyone. So in this video we're going to look at macroscopic balances of mass and momentum. You know that the conservation principles in fluid mechanics are the conservation of mass, momentum and energy. We will focus on the first two. You also know that you can express these conservation principles in integral form, so looking at the finite volume of fluid and doing your balance across the inlet and outlet section, or by looking at local forms and using differential equations. So what we'll do first is to start from the macroscopic balance, and we start from the macroscopic balance of mass. Now, you see here the control volume of interest with the section 1, which is an inlet, and the section 2, which is an outlet. We can assume that the fluid will have a density ρ1, a scalar velocity v1, and a section S1 for at this inlet section, and similarly we can say ρ2, v2, S2. Something interesting you see here, streamlines. What are streamlines? So these are family of curves which are instantaneously tangent to the velocity field, and so this will give you an idea of the direction of the flow from the inlet to the outlet. Okay. Now, to establish our conservation balance here, we have to define what is our quantity of interest. And so you probably remember when we were talking about the mass fluxes, the convective fluxes, that we defined the convective fluxes of mass as the product of rho v. How did we do that? Well, we considered a cylinder with particles moving at a certain speed uniform at section 1, and then we chose section 2 in a way that the length of this section allowed, after a time delta t, all the particles to cross section 2. So we had a length delta t times v, so that all the particles moving at speed v would have crossed in a time delta t the section. Okay, and then we defined this convective mass flux as the mass in the cylinder divided by the delta t and the section, and so we ended up with rho v. Okay, now the quantity that we want to conserve here is the mass flow rate, and the mass flow rate, which we indicate with m dot, so this is the mass flow rate, is nothing but this convective mass flux times the surface. So it's the product rho v times s. Okay, so this is the definition of the mass flow rate. The units of the mass flow rate are kilograms per second. Okay, and so you also realize that this is a very easy quantity to measure because you only need a scale and the chronometer. Okay, so we have defined our quantity of interest. We have to establish now the conservation principle. And so let's start from the simple case that we have a steady system. So steady means that all flow properties do not change in time. So in other words, all the time derivatives will be equal to 0. Then in that case, if we had to just indicate the conservation of mass principle in words, we would say that the mass entering the control volume equal the mass leaving the control volume. Okay, because of course we are not in the context of nuclear reactions, and so the mass must be conserved. And so in mathematical terms, it means that the mass flow rate at the inlet equal the mass flow rate at the outlet, or in other words, that the mass flow rate m dot is a constant. Okay, so this is a very simple mass balance that we can establish for a steady system with a single inlet and a single outlet. Okay, uh, very good. So now, what happens if on the other end we are in a more general case? Which means, for instance, an unsteady problem with the velocity field which is not uniform. So how does this balance changes? So of course we have to consider uh, the um, the fact that the mass in the volume can change in time, and so we will have an unsteady term, and so the accumulation, which is of course can be negative or positive, of mass in the control volume, will be simply equal to the difference between the inlet mass flow rate and the outlet mass flow rate. So let's take the very general case that density is constant but the velocity is not constant across the inlet section. Then the mass flow rate in the inlet can be expressed as rho times the integral over the section S of V ds. Okay, and so this is what we get at section 1. And then we have to remove, of course, the contribution at the outlet, and so this is a rho, then the integral VDS over section S, and this is done on section 2. Excellent. So now that we have that, we can also introduce an average velocity that is 1 over S integral VDS over the section. So this is the average velocity on section S. Okay. Now with this definition, we get a final formulation of this conservation principle of the conservation of mass, which is dm over dt rho vs 1 minus rho vs 2. And of course here we are considering the average velocities on the section S, and we consider the scalar value of the velocity because this is a scalar balance. Of course, from this general equation, you also realize that in case the problem is steady, this term is equal to 0, and then you would recover, of course, the steady balance, which is mass flow rate at section 1 equal mass flow rate at section 2. Okay, so we established the macroscopic mass balance. And now we want to do a macroscopic balance but of momentum. And so to do that, now let's move on. To do that, we have to do some simple consideration before. So momentum balance. So while we said that for the mass cannot be created or destroyed, it must be conserved, of course, except nuclear reaction. For momentum, we know that momentum can be created and destroyed. And this is because momentum can be created and destroyed due to the forces which are applied to the control volume. Okay, so this is a very important let's say, consideration, because it means that in a steady case we cannot simply say that the momentum entering the control volume equals the momentum leaving the control volume. Okay, because this difference will be equal to the sum of the applied forces to the control volume. Okay, first of all, we have to define what is the what can be these forces, but even before, what is the momentum flow rate through a section, okay, per unit time. So momentum flow rate So similarly to what we have done for the mass flow rate, so the momentum flow rate that we indicate with Q, capital Q, and then we have a dot, is the product of the mass flow rate times the velocity. But so, as I said before, momentum can be created because of the forces applied to the volume. So this balance that we are going to write here, it's not a scalar balance, but it's a vector balance. And so here, this is a vectorial quantity because we have to consider the fact that the velocity is a vector. And so this generation of forces must account for the vectorial nature of V. So in other words, we can also write this rho V square times S, where in this case, this is the module of the vector. While S is a vector, so it's the surface vector with of course module equal to the scalar surface, and the same direction as the fluid flow. Okay, so nothing very special. What is important here to remember is that this is a vectorial equation. So Q dot, which is our momentum flow rate, is a vectorial quantity. So it's the product of the mass flow rate times the velocity vector, or rho v square times the surface vector. Okay, this is for the momentum flow rate. What about the sum of applied forces? So when we did our introduction to the fluid mechanics, we said that in practice we can have surface forces, so the forces on the wall, so the shear stresses. We can have the pressure forces, and we can have the gravity. So if we look at our specific problem, remember we have an inlet section 1, we have an outlet section 2. So we basically have to consider the forces that can be exerted on the fluid and by the fluid in this configuration. So as I said before, we can have three kinds of forces. We can have pressure, we can have forces on the wall, the shear stresses, and this can be, and also the gravity and other volume forces. So for the configuration at end, this means that the forces that we consider, and remember this is also a vectorial quantity, will be a pressure times a section. So pressure is a force per unit area, then I have to multiply by the section. Then the pressure that I have on section 2, okay, then the force of the walls, and then the gravity forces. Okay, so now you have noticed that I have put some signs. Okay, now of course for these signs there is a convention, and the convention is the following. We consider positive the forces that actually make a work on the system. So you see the fluid that is entering the control volume here is actually making a work, is actually exerting a work to entering the control volume. So it's exerting a work on the fluid which is in the control volume, and so this contribution is positive. For the pressure contribution on the outlet, this is done by the system on the outside of the system, and so this is a negative contribution. The contribution of the gravity forces is also positive because it's on the system, and the force on the walls we consider let's say we consider that the contribution is also done by the system, and so we take a negative contribution in this formulation. Okay, but this is just a convention. We are considering positive the forces which are made on the system, and negative the ones which are done by the system. Okay, so putting these all together, we said in words, in fact, that the difference between the momentum flow rate entering and leaving the system is equal to the sum of applied forces, where again we consider positive the forces that are responsible of a work done on the system. So the pressure contribution in section 1 is positive because it's doing a work to enter inside the system, while we consider negative the forces which are responsible of a work done by the system. Okay, so if we put all of this together and we try to put in equation the words that I just wrote down here with the orange Bic pen, so what I have is the following equation. So I have a Q dot 2 minus Q dot 1 is equal to the sum of forces applied, and these are all vectorial quantities. Okay, so let's express that further. So I have M2 V2 minus M1 V1. This is equal to P1 S1 minus P2 S2 minus Fw, forces on the wall, plus gravity and other volume forces. Okay, so now what I can also do here is that I can use the delta Kronecker. So it's delta 1 2 of phi means simply phi 2 minus phi 1. Okay, so I use this symbol here, and so I could rewrite everything as delta 1 2 rho p square plus the pressure times the section. So this is the difference between these two contributions at section 2 and section 1. This is equal to minus the wall forces and plus the gravity forces. Okay, so this is the steady momentum balance for a control volume. Okay, now in case we do not have a steady process, okay, so in that case we have to consider the time derivatives. And so in this case we should consider the time derivative of momentum in the control volume. So what is the time derivative of momentum in the control volume? It's simply a d over dt, the integral in the volume of the momentum, so which is rho v dv. So this is a small v and this is a vector. Okay, so you see that this is expressing in fact the variation of momentum inside the control volume. Okay, so what I have to do here, I simply have to then indicate that this variation in the control volume, so you see by the way that the product of rho and dv will be the mass, so you're actually considering the variation in time of mv, so this could be also written as d over dt dm times v. Okay, good. So the variation in time of the momentum inside the control volume will be then given by the momentum flow rate entering the control volume, the one leaving, and of course all the applied forces. So we rewrite all the terms that we have written before. So it's m1 v1 minus m2 v2, and then of course we have the force terms, which are the following. So we have plus p1 s1 minus p2 s2 minus fw plus fg, and I have to indicate that these are vectorial quantities. Okay, so let's continue. Then I have d over dt integral of rho v dv. I do the same expansion that I did before. So what I mean here is that I remember that m dot is the product rho v times s. So what I have here is a rho v squared. This is the modulo of velocity plus p in section 1 times s1 minus rho v squared plus p section 2 times s2. Then I have the wall forces, and then I have the volumetric forces. Okay, and finally if I use again the Kronecker delta, so if I use the symbol delta, I get the final expression, which is d over dt integral on the volume rho v dv is equal to minus delta 1 2 rho v square plus p times the section minus fw, the wall forces, plus f gravity. And so this is my general momentum balance applied to the control volume. again, as we did for the mass balance, you see very clearly that if I have a steady process, I go back to the steady formulation. So all these d over dt terms will be equal to 0, and so I just recover the steady formulation that we found before. Okay, great. So we for this video, that's all. Now in the next video I will show you how to find the conservation of mass principle, but with the differential approach.